Hello there, Mr. Sutton here, bringing you the Algebra 2 Honors 11-4 lesson on finding sums of infinite geometric series. So in this one, we're going to be finding sums of infinite geometric series, as the title suggests, and among other uses, this will allow us to convert repeating decimals into fractions. So you might be wondering, how are we going to add together an infinite number of terms in a geometric series? Well, let's take a look at this. We'll start by talking about the sum of a finite geometric series. Seems like a good starting place. So recall that that was s sub n equals a sub 1 times 1 minus r to the n, all over 1 minus r. We used this a few times in that last lesson. And we're asking now, what about an infinite geometric series sum? What happens specifically if this n value, which represents the number of terms that I'm adding together, what if this n value is approaching infinity? So there's actually a few different cases to consider, and it all kind of hinges on the nature of this r value, this number that we keep multiplying by over and over again. Let's take the first case, which is kind of the most common one, which is where the absolute value of this r, because it could be negative as well, let's say the absolute value of this r is bigger than 1, like 2 or negative 3 or something like that. Well, if I take something bigger than 1 and keep multiplying it by itself, that means that this r to the n is going to grow bigger and bigger and bigger. It's just going to go to infinity as n keeps getting larger and larger. So I could rewrite this whole thing, but I could replace r to the n with basically infinity. So if I essentially have infinity or negative infinity over some finite number down here, because r is just whatever it is, that's going to give me an infinite value, which is just a fancy way of saying that our series will have no finite sum. And this kind of makes sense if you just think about what that kind of a series would look like. So this would be like a series like 1 plus 2 plus 4 plus 8 plus 16. Basically, if you had an r value of 2, you just keep adding bigger and bigger numbers together. So of course, that series is just going to go off into infinity as you keep adding more and more numbers. Now, what about the weird case of r, the absolute value of r equaling exactly 1? Well, in that case, 1 to any power is just going to be 1. So you'd have 1 minus 1, which is just 0. And that's okay, except that 1 minus 1 down here would also be 0. So that would essentially give you 0 over 0, which is indeterminate, which means that if you're trying to calculate this sum, this also is not a finite sum. Whatever it is, it's not a number. It's not a single constant. So let's take a look at our third case then, where this r value is less than 1. So now we're multiplying by a number that's between negative 1 and 1, so that every time I multiply r by itself, I keep getting a smaller and smaller and smaller number. Think of the series, 1 plus 1/2, plus 1/4, plus 1/8. Yes, we keep adding numbers, but they keep getting smaller and smaller. In that case, if I take something that's between negative 1 and 1 and raise it to a super large power, it is getting smaller and smaller to the point where it's practically 0. And if this thing is practically 0, then if I was able to go all the way to infinity for this n value, that would mean that I would just have a times 1 minus 0 up here, which would just be a sub 1 over 1 minus r. So this is actually something, right? A1 is a number, r is a number. If we plug those in, we get something else. We get a finite number. This is a finite sum. And in fact, s equals a sub 1 over 1 minus r is the formula for the sum of an infinite geometric series. It's kind of crazy to think that to add an infinite number of things together, something this kind of small and elegant would actually do the job, but it works, and this is all why. And if you don't believe me, we can verify this. So we are here on the Desmos grapher. I'm going to show you kind of a practical demonstration that, yes, if your r is bigger than 1, bad things happen, and if it's less than 1, then you can get a finite sum. So let me set up a series that it won't be infinite, but it'll be close enough. So let me write f of x equals, so I'm going to define a function that has the sum of a geometric series as its output. So I'm going to write sum, S-U-M. I'm going to go from n to, and now my upper limit of summation, I'm going to make that x so that I get to control how big this series is. And then I'm going to put an r value in here. Let me just use 2. And I'm going to raise that to the n power. So this is the series like 2 plus 4 plus 8 plus 16. Now let me go down here and let me just do f of a number. Let me do f of 1. So that would just be 2, right? If I do f of 2, well, that would be the first two terms, 2 plus 4. f of 3, that would be 2 plus 4 plus 8. And I can keep going. Let's amp up this number a bit. Let's make it 10. So that's quite a bit bigger. Let's add another 0, 100. First 100 terms of this thing add up to some enormous number. And if I make that 1,000, well, that just keeps getting bigger and bigger. And if I make it 10,000 terms, well, Desmos just gives up. It is actually a finite number, but it's so big that Desmos cannot even conceive of what it might be. Let's just go back to something less undefined. All right, now what happens if I make this, let's make this exactly 1. If I make this exactly 1, then I'm actually just adding a bunch of 1s together. So f of 1,000 would just give me 1,000, and I could keep going and get bigger and bigger numbers. And that doesn't mean that if I go to infinity, this thing is finite, because I would be adding an infinite number of 1s together. But Desmos can at least handle big series with that. Now let's make this 0.5, 1/2. If I do that, we see that f of 1,000 is just 1. I mean, let's just go back to f of 1, right? So there's 1/2. Here's 1/2 plus 1/4, 1/2 plus 1/4 plus 1/8, and we can keep going. Now if I make this 10, 100, 1,000, 10,000, 100,000, a million, and you can look at the graph, the sum of this thing is flattening out. In fact, you'll see this if you have any value that's less than 1. It still, if you go out far enough, flattens out. If you make it just a little bit more than 1, then our graph goes off into infinity. So this is a graphical demonstration of everything we did here. So for today, we're just going to be using this formula. There's only one catch. This beautiful formula only works if r absolute value is less than 1. So you have to always verify that your absolute value of r is less than 1 before using your infinite sum formula. Deal? Awesome. Let's keep going. All right, we're going to do a few examples where we are finding the sum of a geometric series, an infinite geometric series, if it exists. Note the wording of these problems. So pause the video and try this one out. All right, so one thing we're going to need for our formula is we're going to need to know the a sub 1 value. Again, we can get that by plugging the lower limit of summation into the summand here. So if I plug in 1 for I, this is just 0.7 to the 0, which is just 1. 3 times that just gives us 3. So that's our a sub 1. The r is the thing that's being raised to the exponent, so that's just this 0.7. Now, with that formula for the infinite series, and we know we need it because we've got infinity for the upper limit of summation, with that formula, we know that we have to check to see that absolute value of r is less than 1. 0.7 is less than 1. So this checks out. This means that we have a finite sum that we can now use our formula to find. Again, we've got s equals a1 over 1 minus r. So that's going to be 3 over 1 minus 0.7. And that's just going to be 3 over 0.3, which is 10. Alrighty, here's a few more examples. Try out example 2, and both of these you'll notice are in just kind of expanded versus the summation form. Pause the video, give this one a shot. Alright, see how that worked out. So a1 is 1. And r, if you just do like 3 divided by 1 here, we see that r is just 3. Now, before you go ahead and plug that into the formula, note that the absolute value of r, the 3 here, is greater than 1. Greater than or equal to 1. This tells us that there's actually no finite sum We could plug A1 and 3 into the formula and it would give us something, but because the formula does not apply in this situation, it would just be a meaningless garbage value. So this means we have to just kind of move on to the next thing. And the next thing is example 3. Pause the video and try this one out. All right, so our A1 this time around is 2. The R value I can get by doing really any term divided by the preceding term. So maybe like 6 over 4 divided by 2. Now 6 over 4 is really 3 over 2. And if I divide that by 2, I'm really multiplying by 1 over 2. 3 halves times 1 half is 3/4. And we're in luck here because 3/4 is between negative and positive 1. The absolute value is less than 1. So we do have a finite sum for this one. So we're going to do A1 over 1 minus R. So 2 over 1 minus 3/4. And that's going to be 2 over 1/4. Same change flip. I've got 2 times 4 over 1, which comes out to the finite number 8. So at this point, you might be wondering where could you use this sum of an infinite geometric series kind of stuff in a real life setting, other than maybe like a cool party trick or something. Let's say that we have a pendulum that's released and swings freely, and let's say this thing travels 18 inches on its first swing, and then on each successive swing it travels 80% of the distance from the previous swing. We want to know the total distance this pendulum travels. All right. So we have this multiplying over and over again by the same number. That's what this 80% sort of thing is doing. This is definitely an exponential sort of function situation. So an infinite geometric series is what's going on here. Pause the video and see if you can find that distance. All right, so we have our A1. That would be this 18. That's our first distance traveled. And then for the R value, what we're multiplying by each time to get the next distance, well, 80%, that means we're multiplying by 0.8. So that's the R. And if you just want to do a quick mental check, 0.8 is less than 1 absolute value-wise. So we are going to get a finite sum when we do this. That would be kind of crazy if this pendulum just went on forever. So let's use our formula, A1 over 1 minus R. So that's 18 over 1 minus 0.8. So that's going to be 18 over 0.2. Now we could do this on the calculator. In fact, yeah, let's do that. So here we go. Let's do fraction 18 divided by 1 minus 0.8. And that all comes out to 90. So hey, 90 inches. For our last mathematical trick, and you probably could use this at a party, maybe like a 5th grade birthday party. We want to write this repeating decimal as a fraction in simplest form. So the key on this one is recognizing that we can actually rewrite this as a geometric series. So that'll be our first thing to do on this one, is rewrite this as an infinite geometric series. And then if we can do that, we can find the sum. Now, how could we actually rewrite this? Well, I could express this as 0.24 plus 0.0024, so that would give me the 2424, plus 0.000024. And I think you can see how we could keep going and account for all of the repeated decimals in this thing in an infinite manner. So yeah, this is an infinite geometric series. We're multiplying by the same thing over and over to get these successive terms. So pause the video and see what we can turn this into. All right, so our A1 value in this case is just this first 0.24. The R value, what I have to multiply to get these two zeros in here, I have to multiply by a power of 10 here. This is going to be 10 to the negative 2 to get this each time. So we're multiplying essentially by 0.01. And you can get that if you want by dividing 0.24 by, or 0.0024 by 0.24. So just verifying this using Desmos, because we can afford to be careful here. That does indeed come out to 0.01. And that's between negative and positive 1, so this will actually have a finite sum, which it should because this number is finite-ish. So we've got a1 divided by 1 minus r. That's 0.24 divided by 1 minus 0.01. And we want to turn this into a fraction in simplest form, so we're not just going to get a crazy decimal out of this. This is 0.24 over 0.99. Now, if I want to get rid of the decimals, I can just multiply this by 100 over 100. So this is really like 24 over 99. And I can reduce this. These are both divisible by 3 at least. So that would be 8 over 33. And if we go on the calculator just to kind of verify that this is a thing, 8 divided by 33, there it is, 0.242424, all the 2 4s. So this is going to wrap up our lesson on sums of infinite geometric series. 8/33 may go on forever, but I cannot. So until next time, this is Mr. Sutton signing off.